Welcome back after lunch. You've got another hour of me, so hopefully you enjoyed the first round. This time we're going to talk a lot more about sort of the outputs of modeling and what you can do in distribution planning, especially with local resources in terms of integrating them within the distribution system and then sort of contemplating and assigning value to their contributions from there. We're going to start with the capabilities by the individual technology. Then we'll look at the value streams and some benefit cost analysis techniques around DERs and electrification. We'll look at hosting capacity analysis and give a really concrete example of what you can do with a really good map, and then get into some of the benefit costs and sort of proactive approach to distribution planning and investment as opposed to sort of the traditional approach, what the potential benefits are, what the potential risks are, and some techniques for sort of how to account for and handle those accordingly. So capabilities by technology, what kind of technologies are we talking about? All kinds of different DERs. We focus a lot on solar, photovoltaic, battery storage is in there, but there's a lot of these that some of the core sort of foundational principles can still be applied to. That said, a lot of the energy and emphasis has been on PV and batteries, so we'll focus a lot of the examples there, but there's a lot of potential in things like demand response or grid interactive buildings or other technologies that may borrow from or use some of these. So when we talk about DER integration, the 1547-2018 standard is sort of the starting point. This defines the specific hardware and interoperability requirements and the inverter requirements and smart inverter functions, and basically that interface between the customer resource or the DER and the utility. It has roles and responsibilities for manufacturers, for utilities, for commissions, for ISOs and RTOs, customers, installers, and just sort of defines what that interface is supposed to look like, what the DER is supposed to be able to do, how the sites are supposed to be designed, and how they behave. This focuses on the new standard, the 2018 version, focuses extensively on both the distribution and the bulk power system and potential impacts of DERs there. It encompasses the entire DER or the entire site, not just the individual sort of components if you have multiple inverters. Can be used for equipment verification or the sort of like whole site plant level, and then defines interoperability and communications, and especially like bulk power ride-through settings. So we'll explore these in a little bit more detail, but this is sort of the overview. So we'll start with autonomous voltage response. Volt-VAR curves, one of the big keynote sort of smart inverter functions, gets a lot of the most discussion. A volt-VAR curve is a customizable curve that lets a DER measure its local voltage and then change its reactive power output accordingly to try to help manage that voltage into the good range and away from the bad range. So you'll see the curve up here. There's a line in the middle where it's just right along zero. We call that the dead band. That is the area in which the inverter doesn't have to do anything with reactive power. Basically, the voltage is normal. There's no reason for it to do anything, so it doesn't have to do anything. Once you start seeing your voltage increase above that dead band, the volt-VAR curve will motivate the DER to start absorbing reactive power to bring the voltage back down. You're trying to get it back towards the dead band, towards the acceptable region. Likewise, if it starts to get too low, the inverter will start injecting reactive power to pump it back up and sort of renormalize it. So that's the function of the volt-VAR curve, very widely utilized and helps to sort of minimize potential negative impacts from DER on voltage and provide some positive benefits too. Volt-watt curve is the second one that exists in the same space. The volt part refers to what it's monitoring. The watt part refers to what it's changing. So volt-VAR monitors voltage, changes VARs. Volt-watt monitors voltage, changes watts, which is the real power. Under this, you have a curve where the DER will start reducing its real power output as you start to get higher and higher levels of voltage. This is intended to sort of offset the voltage increase that comes with DER and is used as a mechanism for addressing overvoltage. Relatively less common, relatively less popular, although it is implemented in a lot of states, because reducing real power output has much more direct impacts on customers in terms of like business case and financial value. So those are the smart inverter sort of functions and standards. Now we're going to start talking about the value streams of these DER to the distribution system and how they can be valued. So DER capacity impact is really the biggest, sort of most keynote one. This is a way of installing DER to reduce the thermal loading on equipment during system peak. So if you had 5 megawatts of load and you add solar that's producing, it reduces the amount of energy that flows physically through that equipment. So it's not loaded as much. It provides some capacity relief. Traditionally, if you have a capacity constraint, the solution would be to build new infrastructure, whether that means replacing the component with something that's rated for higher, or adding a new substation, or transferring load to new feeders. But it's capital investment to provide capacity. DER-based capacity is another way to provide a similar service, although it comes with some differences. The type of DER and its performance matters a lot here. So PV, for example, the generating time has to line up with the system needs. So if your local substation peaks at 3 p.m. when the sun is out, that's great. It's a lot better of a candidate. If it peaks at 8, 9, 10 p.m. at night, there's not really a whole lot solar's going to do for you. Likewise, these other technologies are similar. Battery storage has a lot of potential, but you have to have a mechanism to actually line its performance up with your own needs, whether that's sort of on the demand response side or at the system level, or some more advanced telemetry or controls. Or lining up battery storage is a lot more finicky, really depends on what you're doing. And then there's some considerations for other technologies as well. Reliability comes up a lot in the space of what can DER do for the distribution system. There are some potentials here, but I'll advise some caution as we move through. DER can provide a mechanism for sort of an alternate source when there's a loss of the normal source. So the best example is a customer who has their own home, so like solar plus battery. When you lose the grid source, that customer can sustain themselves with their DER when the primary system is out. That doesn't provide any benefits to anybody else on the distribution system, though. And that's where we have to be careful. Like, customers energizing themselves is good and useful, but that's that customer benefiting themselves. It doesn't sort of appreciate to the wider distribution system. If you want to increase reliability with DER on the wider distribution system, you have to have a mechanism for energizing the whole section of the feeder that's out, or a portion of it, to get customers back on. Locationally specific, like microgrids as an example, is one way of doing this, where you have a specific deployment at a specific area that has sort of boundaries around which customers are planned to be re-energized and how, and using what resources. Absent that sort of specific controls and design, the DER, when there's an outage, are required to disconnect and not operate and not re-energize the faulted portion of the system. So if you don't have a specific sort of microgrid deployment or a design or a plan to do that, you're not going to see any tangible impact on reliability from adding DER. And we'll go through an example to show that in a little bit more detail. But keynote from this slide, SAFE and SAIDI will not go down with more DER penetration, even if customers are doing it themselves. The meter's still dead. So it still counts as an outage from utility standpoint, unless it's being re-energized from a different source. All right, so let's look at a couple of examples that I think will help illustrate this. So this is an example of a residential customer that has a backup system. So you've got your meter there on the dotted line, you have a main circuit breaker. There is a transfer switch in here that will operate and physically disconnect this whole site from the distribution system when there's an outage. Once that disconnection happens, then the solar and battery on the bottom will re-energize all of the local loads and create a microgrid for that customer. So that's how this works. The transfer switch opens. There is no voltage going back to the distribution system. There's no way to re-energize it. It's physically separated. As a result, that meter is still dead. So it's still counted under utility outage statistics. This is a more complicated example with a microgrid implementation. Here we've got 3 different substations, one on the top, one on the bottom, and one on the right side. You'll see the 3 colored circles that show sort of which substation is feeding which area. We're going to walk through what happens when there's a fault. What does the microgrid do? How are customers impacted? So right now, everything in that main line from substation 3 to the left is fed from substation 3. We've got a recloser right now that's closed, and normal operating, everything's fine. And then downline, we've got a microgrid that's not really doing much at the moment. feeding all the way up to those two normally open switches, switch 1 and switch 2, where the feeders back up against each other, but they don't meaningfully interact because there's an air gap between them. So now we're going to add a fault. Something bad happened just downstream of that recloser that we're now showing as open. So that recloser detects the fault, sees the fault current, opens and physically disconnects everything to the left of it from the system. So everything is de-energized. Once that happens, the microgrid DER that's bounded by switches 3 and 4 here detects lots of utility source and will intentionally island all of those customers there in the middle. So everything in that dotted box will see a minor disruption, but remain energized by the microgrid. Everything to the left of switch number 3 is de-energized. They are experiencing an outage. So until something happens, those customers can't be supported by the microgrid. Maybe it's not big enough. Maybe that wasn't the intent. Those customers are out. So now let's clean it up. So now we're the utility responding. We are able to pick up a portion of the de-energized customers now from substation number 1. So you'll see switch number 1 goes from open to closed and now is re-energizing all of that customer group that was out. They never had a problem, but the problem was upstream of them. So we could go to another source, re-energize them from there, and get them back on. The microgrid now has no reason to try to sustain the customers by itself. There's a utility source available. So the microgrid connects back over to the new feeder, helps out and does whatever it's going to do. But the only customers that remain out are those between the recloser and that switch number 4 that's isolated them. So in this case, you're sort of seeing what happens when there's a fault. How does switching restore some customers? How does the microgrid behave? And I think that's a useful example to walk through because a lot of times that sequencing isn't very clear, but the specific groupings of customers are really important to think about. Okay, so potential benefits beyond just distribution system benefits for DERs. Customers may see lower bills based on lower energy consumption. Self-consuming some of their own generation is very economically efficient and energy efficient. Local resources help reduce strain on traditional generation, which is oftentimes difficult to build. There may be capacity constraints from things like data centers that Chris had mentioned previously. Local workforce installing and maintaining DERs is another part of it that may have knock-on economic benefits. And then there's other kind of local state and policy goals that facilitate this that may be realized if you're sort of able to incentivize DER a little bit more. So I'm going to use an Illinois example here of value of DER. This is a program that is intended to, under Illinois law, is replacing the distribution component of net metering with a rebate payment that is intended to be based on the value of that system to the distribution system at the location that it's connecting. So we're going from sort of location agnostic, rate-based traditional net metering compensation to a locational incentive paid upfront when they connect based on the value that's anticipated. So big shift change in terms of how compensation works for these customers. And that came through in the CEJA law from 2023. So this is the sort of framework. There's a base rebate for all customers regardless of where they're at, and then this sort of additive services element for customers in particularly valuable areas, and we'll get into what that means in a minute, but there's some differentiation as well. So this is straight from the report that was filed and sort of how different methods for trying to calculate the value of capacity and thus the value of additional capacity that's enabled by DER. And there's a lot here, but sort of there's two real ways to do this, sort of in the same way that you see with forecasting. On the left side, we have our sort of bottom-up approach where the distribution utility will flag all of their capacity needs over the next however many years, and then build those up and say, okay, we have this many needs in this locations in these areas. The amount of capacity we could add from solar would be this. The amount of cost we would incur building infrastructure to support the anticipated load growth is Y. That avoidable cost or deferrable cost is how you kind of generate the value. So you start from the specific assets that are overloaded, go through the process of doing all this math to say how much is individual DER worth at each location, and then build your sort of rebate values from there. Very granular, very good at isolating marginal costs and benefits. but it's really hard. First, it's limited to whatever the time frame you're looking at is. So if you're looking 10 years out based on your forecast, and these things are going to connect for 25 years, and you're trying to compute and calculate their compensation over that whole window, you may be missing some years on the end. The second, it's based on the forecast, which has its own challenges that Chris kind of mentioned. And then finally, it's based on very sort of inaccessible utility planning information and standards and proposals. It gets very complicated very fast to try to calculate this in any sort of meaningful sense. So bottom up is good and accurate, but has its own sort of challenges. On the right side, this other approach is sort of systematic, top-down approach, using things like FERC Form 1 data that say, well, in the last 5 years, this utility has spent this much money on capacity. We expect this much additional growth in this time period, and thus the kind of cost of capacity is a certain value. So the value of avoided capacity is sort of worth that from DER. That has a lot of appeal. It's a lot easier to do math on and to administer. You don't have to do this sort of granular locational analysis, but you're also including a bunch of stuff that's not really deferrable by DER. So a lot of investments are for reliability or for redundancy or for asset health. And that may get classed in the FERC data as capacity investment, even if you're not trying to add capacity. So there's a lot of stuff in there that gets included that is not actually beneficial or doesn't actually accrue to these DER. And consequently, it tends to overestimate the actual value that avoided capacity would have. So this is the central tension in sort of how to approach this. There's goods and bads from both directions. Most recently, we had this filed to look at what are the benefits and costs to all the different participants. So we have 3 different tests that they're looking at. The first is the participant cost test, which is if you are a person considering installing a DER, do you have enough economic incentive to adopt, right? Does it make financial sense for you to buy a new DER as part of the program? You'll see on some of these, there's net benefits. It's based on the cost of the resources and the overall magnitude of the compensation. The second one that they looked at was the ratepayer cost test, which is, does this program tend to increase or decrease rates, like relative to what would have happened otherwise? And then the third one is the total resource cost test, which is sort of from the societal perspective, are there net benefits to that kind of program or that kind of compensation? So these were the results from E3's study that are publicly filed, showing pretty significant net costs to ratepayers for these, and in a lot of cases, sort of shortfalls on the potential benefits, which basically means the classical net metering approach and the existing sort of base rebate floor result in that cost shift from those customers to ratepayers, which is always present, but is sort of the magnitude and how much is a big part of it. So in trying to decide what to do, like sort of the keynote elements were showing that these cost shifts happen to non-participants, but there are locations where it may be not true, right? They're doing a system level analysis. If you pick the right 10 to 15 feeders where there are actual capacity needs, there are much more high concrete savings that can be realized. This is sort of the same concept as non-wires alternatives, but sort of backed into from a programmatic approach to customers adding DER rather than specific procurements. So they also, kind of what we had talked about, recognized that reliability and resiliency benefits sort of accrue to the individual who has the DER, not necessarily to the broader set of stakeholders who are paying rates, and thus kind of wasn't flagged for additional compensation. Okay, so that's sort of value of DER in a nutshell. I would encourage you to look at some of the foundational pieces and some of the dockets. There's a lot of good discussion. It's a relatively dense topic, but that's sort of the overview and the current status in the work in Illinois. So we're going to shift gears a little bit and talk about hosting capacity, which a lot of you guys are probably familiar with. We're going to look at both solar and EV from sort of a load perspective as well. So what is hosting capacity? This is the amount of load or the amount of generation that can be added to the system before you cause a violation or before you require some sort of system modification. The same concept gets applied both to load and generation, although the constraints that you're looking out for and the types of system upgrades may vary just based on what sorts of impacts are anticipated. Load capacity maps are relatively less common. The DER had kind of a head start in the market in terms of needs, but the load growth and supporting like electrification and charging hubs and that kind of stuff have seen a lot of growth in the load capacity map space. So why do utilities perform hosting capacity other than where they've been ordered to do so? First, it helps aid developers in decision-making for new projects when they're trying to find a location that's going to work where they can connect their new solar facility or their new 5 megawatt EV charging depot. Knowing the grid conditions and what sorts of capacity upgrades and constraints exist is really helpful in planning those projects. If you do it right, hosting capacity can help reduce the application screening time and increase the success rate of applicants. The idea is if they have more information about what they're going to face in the process, they will focus on sites that are actually likely to make it through the process rather than just submitting a bunch of applications to see if they can sort of squeeze something through without really knowing what's going on there. And then finally, they can be used to aid in distribution planning. Once you know where your constraints are, you can sort of jumpstart to line those up with the forecast and then start figuring out where you might need to make investments and how. So constraints that are considered typically, hosting capacity considers thermal overload both for load and generation, and then more for the generation side, things like overvoltage, reverse power flow protection, or system protection. This is an example from here locally from Excel's map in Colorado. There's a lot of maps linked throughout here. There's a lot of good maps out there, more than there used to be. So we mentioned hosting capacity maps. The goal is to lower application volume by increasing application success rate, basically directing applicants to areas where there is more capacity available, where there's sort of less of a shotgun approach to just trying to find a good site, and sort of it also helps drive down the cost. The most annoying applications to study as a planning engineer are the ones that you know aren't going to work, because it's a lot of work to try to model everything and then figure out how to try to make it work and what kinds of upgrades you might need, et cetera. If they apply in an area that has capacity, those go through the modeling process a lot faster because you don't have to try to model those like corrections and edits and that kind of stuff. Use cases for these maps from a developer perspective, again, understanding potential upgrade costs at the varying DER sizes they may be considering. So if you want to have at a specific site, do I want a 2 megawatt system, a 5 megawatt system? That may depend, right? I may be good with both. I might want to get as much as I can. So knowing what that size looks like is important. Understanding the interconnection timeline based on the queue size. If you know you're going to have to wait 6 months in line before all the existing ones are through, or that's like a 10-year time frame based on the volume that's ahead of you, or if there's nobody ahead of you, that's a really useful thing to know when you're trying to decide which sites to pursue and sort of how long it's going to take to get connected there. And then finally, determining the overall feasibility for the site based on hosting capacity alongside the other constraints that they're considering. Things like land and zoning and all the things that go into picking and developing a site other than just distribution utility constraints. So I've linked a good Synapse report here showing sort of what types of data may be available at different levels of granularity, things like load profiles, substation data, queue DER. And we'll go through an example to show this in a little bit more specificity. So one of the most important questions I think to take out of this session is, how do I know if a hosting capacity map is actually effective, right? There's a lot of effort that goes into standing one of these things up. How do I know if it's actually going to be useful to the people it's intended to be useful for, if it's going to actually be able to achieve these sorts of things that I'm talking about? Well, there's a couple of factors, and we'll do an example walkthrough afterwards to show it. But basically, is the information that's provided locationally specific enough to be useful? Are you looking at results for a couple 100 feet by a couple 100 feet box, or are you looking at one result for a 25 square mile area, right? One of those is a lot more useful than the other. Is the information up to date enough to be trusted? If you look at a hosting capacity map and that data is 3 years old, it doesn't matter what the map says. Like, there's nothing useful you're going to take from that, right? So being up to date is really important. And then finally, is the information provided enough to empower developers to cite and size their DER effectively? This is a much bigger sort of challenge, but it's also really important, right? That's what we want to do. We want to give information out to help developers find and pick good sites and interconnect. So in general, maps that have larger geographic area blocks, less information, or are updated relatively infrequently are less effective. Maps that have smaller geographic blocks, more or most or all of the relevant information, and relatively current information are more effective. So all important takeaways. Some of you are going to be like, I don't believe you. Can this map actually be useful? So we're going to do an example. This one is from Minnesota. This is Excel Energy's map from Minnesota. And I'm going to talk about the characteristics, and then I'm going to walk you through what I can do with this map data without knowing anything about the distribution system other than what's on here. So a couple of things that you'll see. First, there's a whole bunch of stuff. There's a bunch of lines, there's a bunch of areas, there's a bunch of sections. There's a lot of data here. That's always a good thing. Second, if you look at the geographic section, these blocks are relatively small. The results are within a couple hundred feet by a couple hundred feet geographically, which means there's a lot of really good resolution in there. There's a lot of variation based on where you're at. That's a really good sign. So we're going to dive through the big box of information on the right. But from this, I can tell you what size of project I would recommend, how long I would expect the study to take, what kinds of system upgrades you're likely to see, and how much of a line extension should you expect to get there, and what does that cost look like. This data is about 6 months old. That's really good in context. Faster is always better, but not always necessary. There may be like triggers for updating based on changes and things like that. So 6 months is not bad. So let's dive into this monstrosity of data here on the right side and try and make some sense of it. So I made some big claims about being able to tell you about picking sites and sizes and everything off of this. So we're going to walk through what data is on here and how does that translate. So if you look on this box on the top left, you have all the different conditions that the utility is testing hosting capacity for. So at 8.1 megawatts, there is a primary overvoltage issue. At 4.9 megawatts, there is a thermal discharge limit issue that sort of blocks that. The most constraining condition here is 1.2 megawatts for anti-islanding. So from that, I can sort of glean this information that my first constraint I'm going to hit is at 1.2 megawatts, anti-islanding. Excel's standard for anti-islanding is voltage supervisory reclosing, which has a cost somewhere between $200,000 and $400,000. So I should expect to have to pay that cost if I'm going to go over that size. How much more over that size should I try to go? Well, my next constraint is at 4.9 megawatts, and that's a thermal overload. Thermal overloads are really expensive. I probably don't want to run into that condition. So I probably want to size my site 4.8 megawatts, and I probably want to expect to have to pay somewhere between $200,000 and $400,000 plus whatever the line extension is. That sort of information is really useful to see not just how much capacity is available, but how should I try to sequence or size my project? What am I going to run into at these different sizes? In the bottom left, understanding project timeline. I can see we have the amount of installed DG capacity that's already there and the amount that's in queue on that area. There are no applicants in front of me. So if I apply, I am first in line. I should expect that study to go relatively fast because I'm not really waiting on anything. And then in the bottom right, let's say my site is not necessarily touching the existing distribution infrastructure. I might be a little bit away. I might need a line extension to get there. Well, I have enough granularity that I can see where those distribution facilities are, how long that line extension is going to be, and what that cost is going to look like also. So I can get a lot of information about how I should design my project, what I should expect in the process in terms of cost and timeline. So if you have a good map, these are all things that can be synthesized out from that data. All right, so that's our hosting capacity section. Now we're going to look at proactive investments and what that is and means and how that sort of contrasts with a lot of existing utility investment process. So what is a proactive investment relative to like a reactive investment? Traditional capacity planning is reactive. It is system changes have been relatively slow. I'm generally acting on relatively high confidence information. So I know what my load additions are for specific large customers that are adding spot loads like a new factory or a new grain bin or whatever. I know where my DER interconnections are because they're applying and coming in that way. So I'm acting on information that's already come in. And then I have a sort of short-term load growth forecast for where some of the economic development might be or where other changes might be happening. All of this information is in the next 1 to 3 years. That's also the timeline it takes me to execute a distribution upgrade. If I'm building a new substation, I'm somewhere between 2 and 5 years out is when I need to start making an investment. But I'm making that investment in reaction to known or relatively short-term information that I'm acting on with high confidence. The traditional approach can limit the speed of new growth if that happens faster than you can build infrastructure. So if there's a 5-year lead time for a new substation, but you're seeing growth come in much faster than that, that's going to impact the ability of that new load to connect. Proactive planning, in contrast to the sort of traditional process, builds for load or DER capacity based on longer, further out expectations in terms of growth, more of a forecast-based approach. The existing also utilizes forecasts, but you're using much shorter timeframes and sort of acting at the sort of just-in-time is how I would describe the traditional process, whereas proactive is you're trying to get out in front of that potential growth. So what does this look like in terms of goals and risks? Traditional planning, the goal is to minimize the risk of unutilized investments, right? In getting it through and getting recovery, you need to demonstrate that it was prudent, that it was used and useful, that you needed that capacity, and that's why you built it. So the process is geared around that. How do I minimize the risk that this thing doesn't get utilized? I have traditional ways of doing cost allocation based on all of the things that come in. So I have the rate base for like baseline growth. I have spot load, things like contribution and native construction, where they may have a portion of the cost of expanding the system that they're responsible for. And then for DER developers, a lot of times it's cost causer pays. So whoever is coming in to interconnect is sort of on the hook for any system changes needed to support them. The risks within this traditional process, as I sort of mentioned, is the construction timeline. Historically, 1 to 2 to 5+ years on infrastructure build, depending on how long it takes in a specific area. But historically, adding a new giant load is also a long timeline thing. You're not getting a new 5 megawatt manufacturing facility stood up in 6 months, right? That has a long build out time too. So that risk hasn't historically been huge. It's been there, but it's not been a primary sort of driver. On the flip side, this sort of proactive planning approach flips both of those around. So in the goals now, the goal is not to block load or, in some cases, PV development or other DER adoption, not to have the grid act as a sort of barrier to adopting these technologies. So in order to do that, well, construction, one of the big reasons for this, construction timelines for batteries and EV charging and PV is much, much, much faster. Right, you can stand up a new larger EV charging hub at 5 megawatts much faster than you could build a 5 megawatt factory load. So the timelines have shifted, the risks have sort of shifted accordingly. But the benefit and the use case for this proactive approach is to get out in front of that fast growth and have that capacity there and ready so that those customers aren't waiting 3, 4, 5 years to build out their infrastructure. This comes with additional risks. First, the risk of underutilized investment. The reason the process was designed how it was is so that we minimize the risk that it doesn't do anything useful when we go to put it in rates. So changing that process means sort of re-grappling with this idea of risk of underutilized investment. You're also much more reliant on the accuracy of these forecasts, especially as you're looking further out into the future. A lot of the uncertainty and things that Chris talked about, if you look back 10 years from now, or 10 years ago, and look at what the forecasts were 10 years out, I guarantee you there is a gulf between those two realities, right? So this risk of what happens if the forecast doesn't materialize in the way I expect, or at the location that I expect it to, or at the time I expect it to. These are all important risks in sort of deciding to make these sort of proactive investments. Once we're even past that, the cost allocation piece also comes back into play, because since we're not waiting on those customers, it becomes much more difficult to assign specific costs to those. Think of DER. If you build that capacity out and it already exists, there's no interconnection cost. But if you're building it out in advance, you can't sort of assign that to a customer that hasn't connected yet. So these sort of traditional cost allocation approaches may not work, or may need to be adapted to be able to work for these proactive investments. So these are sort of the key drivers and tensions between reactive planning and proactive planning. And I think it's useful. These are not two different ways to do planning, or two different sort of, we can either be reactive or we can be proactive. There are going to be a lot of investments that should follow the reactive process. The proactive process can be used specifically when you have a specific need and a specific potential risk that you're trying to avoid, or a specific level of confidence in a specific area. So it's not necessarily always do one or always do the other. This is a new tool that you can use where it makes sense to help sort of get some of those grid barriers out of the way, where you can minimize that risk. So we'll dive in a little bit more on some of these cost allocation challenges. For large load customers specifically, these customers generally have at least some portion of the system upgrade that they're responsible for, usually with like a revenue offset for anticipated contributions into rates. Contribution native construction is sort of the common terminology here. If a large load connects in an area that's had a proactive upgrade already built, it is hard to determine and recover what they would have paid for the capacity that was put there for them, right? Because you didn't get them to sign anything initially, you built it out. Now you have to have a new mechanism to try to sort of recoup any of that cost that they would have borne, but they didn't. Similar on the DER side, larger DERs often bear all of the costs of hosting capacity upgrades to accommodate their interconnection. There are cost allocation challenges to rate basing any hosting capacity upgrades at all in a lot of states. Specifically, if a large DER connects in an area that you've built out, DER capacity is really hard to recover their contribution, because there's no cost causer for them anymore, because it's already been built out. So to adapt that, you have to sort of grapple with that. A sort of lesser known impact here that I think it's important to highlight. Proactively building out capacity reduces the likelihood that people and customers will use other methods to try to avoid those capacity constraints. So flexible interconnection as a big one here. Flexible interconnection attempts to maximize the amount of use of the existing infrastructure. How can I connect the most things without needing a system upgrade? If you build all that capacity out in advance, there is no sort of structural incentive for anyone to use a flexible method, even where they could, right? So that's another, there are ways to grapple with this, but it is sort of a natural outcropping of this method that you have to deal with. What are the potential solutions? So I've alluded to these a little bit, but tracking for large load customers, tracking large load interconnections in areas where proactive investments have been made, so that you can get that sort of contribution they would have made in those areas after they connect. They're like, look, if you're connecting here, we built this capacity out already. The cost to interconnect as a result is this, instead of it being sort of reactive. There are some ways to apply traditional cost allocation mechanisms here, whether you're sort of still allowing for some sort of revenue offset or expected contribution. It gets messy, but there is some ways around this. For DER interconnections, incorporating proactive investments within existing or sort of proposed mechanisms for doing DER cost sharing is reasonable, sort of depending a lot on individual states. I think it's worth determining if it's reasonable to socialize some costs, especially for feeders that are effectively closed to new applicants, where there is a bottleneck that exists that no individual like residential customer or other is going to pay for. that's a useful thing to think about in this space of building out capacity before you have that specific demand. And then tracking, again, in these areas where these investments have been made, tracking these interconnections and recovering at least a portion of those costs from the interconnector that's coming in afterwards, rather than waiting and trying to do it before. And then on the flexible interconnection side, customers that utilize flexible methods could be, for example, exempted from any kind of cost contribution towards the upgrade that's already been made, or see it reduced, or see some kind of additional incentive to sort of use this mechanism, even when they're not necessarily avoiding a specific cost. So I talked a lot about potential risks. There are some strategies to minimizing this risk if you're going to use proactive planning for specific investments. First, I strongly recommend only utilizing it where you specifically need it for specific goals, whether that is improving investment efficiency and reducing life cycle cost. So if you're going to replace a transformer for maintenance, if you look out 5 years, you need to upgrade from, it's a 14 MVA now, you may not need to upgrade it at all. If you look out 10 years with a lot of electrification, you might need additional capacity. Now might be the time to pull the trigger on that additional capacity, because you're only sort of adding that incremental marginal cost of the upsized device, versus if you have to come back later, now you're taking an outage, now you've got a lot of labor associated with it. So if you can optimize across the life cycle of the investment, it may make sense to think a little bit further ahead. And this is a relatively common, like, historical utility practice, sort of sizing for expected life cycle, but just sort of acknowledging that that is a thing and comes with additional risk, and talking about it in that way, I think, is still useful. The second two are sort of tied. Preventing the system from blocking expected growth, realizing like state policy goals on adding EV charging or DER, especially where connection timelines are long or capacity upgrade construction times are long. Not having the grid sort of get in the way of that is a really good policy driver that may make that additional risk worthwhile. The third one is to sort of spread out some of this investment over time. If you're expecting sort of a cliff of new EV growth or new heat pumps or like new spot loads 5 years out or 10 years out, there's a limit to how many new substations you can build in a year, both in terms of the resources you have on hand and just the physical number of elements that you can take out within the individual system without dumping customers. So spacing that out and spreading that construction timeline out, or spreading the rate impact out over a longer period, may be desirable. So these are some specific cases where it may make sense to use this kind of investment where that additional risk is justified. I think it's also useful to focus on areas that have relatively high confidence in the forecast. To me, this means residential and small commercial. Law of large numbers says the more of a thing that you have, the more likely it is to sort of follow a regular, predictable distribution. 1,000 residential customers are a lot easier to predict than one large load, right? So areas where you have high confidence in the forecast or can sort of quantify the level of risk effectively are areas where I think this makes more sense to do. And then also projects with multiple benefit streams, places where you're not just buying capacity. So whether that's reliability improvement or getting a new asset, improving asset health, other types of investments, it's worth sort of counting those and thinking about, if this capacity doesn't materialize, what else am I getting from that investment, and is that worthwhile? And if the answer is nothing, it may make sense to hold off until you're a little more certain. But if that's an investment you might want to make anyway or might be competitive, that additional sort of benefit from proactive might push it over the hump. And I'll probably skip this in the interest of time, but basically, like, small commercial customers are much easier to forecast. Upgrades for those customers are already rate-based, especially for loads, so it doesn't impact the cost allocation piece as much. Whereas like large load customers come with a lot more challenges, both in forecasting and cost allocation, that I think, not that we shouldn't do it for them or consider it, but if you're just trying to start out and identify these areas, there's a lot less hurdles to jump over to do this for areas where small customer growth predominates. And then just diversifying benefit streams, again, thinking about what all kinds of benefits you would achieve from doing a project and how that can help sort of mitigate the risk that it's not useful if that growth doesn't materialize like you expect. So closing out, actions that state regulators can take, I'll highlight just a couple. Investigate current mechanisms for DER services and value of DER. Review hosting capacity map requirements and the information that's there, and think about how useful that is in the context of a developer. For state energy offices, providing guidance on state priorities or program information that may feed into like proactive investments. A lot of times policy goals are an important element there. And then similar on the advocate side. Questions that state can ask, what compensation mechanisms and value streams may be suitable for DERs in your given state? How effective is the hosting capacity map information that's provided? How do utilities plan and prioritize capacity investments today? And then sort of how would existing cost allocation frameworks in your state impact these proactive investments? So I recognize there's a lot here. There's a lot to think about. We're just giving kind of a broad sampling of some different DER-related topics in planning. I'd encourage you to also go back through the links as these things come up. A lot of this may sort of migrate out of the brain, but there's a lot of good reference material and a lot of stuff out there to base this off of. All right, and that's all for me.
Great.